Okay, now let's move on with the discussion of the point groups. We have finished the discussion of the low symmetry point groups and the high symmetry point groups. And we have started to discuss point groups with intermediate symmetry. And we have begun discussing point groups that have one proper n-fold axis, and we call these point groups the rotational groups. So in the most simple case, our molecule has only one proper rotational axis in addition to the identity and no other symmetry element. Okay, that's for instance the case for the hydrogen peroxide molecule, and the hydrogen peroxide molecule therefore belongs to the cyclic group Cn. So these have only rotational axes, only one rotational axis, but no other symmetry element. Then we looked at the pyramidal groups. So the pyramidal groups are denoted C and V, and all molecules that belong to the pyramidal groups are derived from an n-gonal pyramid, whereby n stands for the number of corners the base has. So when n is equal to 3, we have a trigonal pyramid. When n is equal to 4, we have a tetragonal pyramid, and so on. So an example for that is the molecule NH3. It belongs to the point group C3V because we have a C3 axis here and 3 vertical mirror planes in addition to that. Okay, and then last but not least, we looked at a special case of the pyramidal point groups, which is the linear point group C infinite V. So in this case, n is infinite, and basically all the molecular structure derived from a cone. So a cone has a principal axis with infinite order, and now we have an infinite number of vertical mirror planes in addition to that. So all polar linear molecules like CO, HF, N2O, and HCN, they belong to that linear point group C infinite V. So now let us discuss additional new point groups that we didn't discuss before. The next kind of point group is the reflection group CNH. So in this case, we do not add a vertical mirror plane to the principal axis. We add a horizontal mirror plane to the principal axis. So the horizontal mirror plane must stand perpendicular to the principal axis. So when we have the point group CNH, then we do not only have a horizontal mirror plane in addition to the principal axis, we also have an improper rotational axis that has the same order as the principal axis. So an example of a molecule that belongs to a reflection point group is the trans N2F2 molecule. So the difluorodiazine molecule, the trans form of it, which you see here. So you see that this is a planar molecule, if you will. So all the atoms lie here in this plane. And this plane is at the same time a horizontal mirror plane because this plane stands perpendicular to the principal axis, which is in this case a C2 axis. So in addition to the identity, we have the C2 axis and a horizontal mirror plane. So we must have an S2 axis in addition to that. Now remember that an S2 is the same as an inversion center, and we can see that inversion center very easily. It's here in the center of the molecule. So as we move all the atoms through that inversion center to the other side, these two fluorine atoms here get swapped up, and these two nitrogen atoms here also get swapped up. So these are all the symmetry elements that exist in this molecule. Okay, so now we have discussed all the rotational groups. Now let us look at dihedral groups. So the rotational groups have a Schoenflies symbol that starts with the capital letter C. The dihedral groups start with the capital letter D. So what the difference between a rotational group and a dihedral group? When we have a dihedral group, then we also have one principal axis. But in addition to that, we have C2 axes, okay? And the number of C2 axes are the same as the order of the principal axis. And the additional C2 axes, they stand perpendicular to the principal axis. So in the most simple case, there are no additional symmetry elements, but the principal axis and the NC2 axes. So in this case, we have point groups of the type Dn. Okay, so an example is this molecule here. So this is a tris oxalator iron complex. So we have here an iron in the center, and we have here 3 oxalate ligands that bind to the iron center. So overall, the iron is octahedrally surrounded by 6 oxygen atoms, but the shape of the molecule, the point group of the molecule, is not octahedral OH. It is D3, and that's because of the relative orientation of the 3 oxalate ligands relative to each other. So now, because of that, we have D3 symmetry, and that means that we have here a C3 principal axis, okay, that stands perpendicular to the paper plane. And now, in addition to that, we have these 3 C2 axes, okay? And these 3 C2 axes stand perpendicular to the C3 principal axis. They're actually all in the paper plane. And they bisect the angle between, well, 2 oxalate ligand, and they go through the carbon-carbon bond of the 3rd oxalate ligand. So we can briefly carry out the symmetry operations and see if the molecule superimposes. And you see that when we carry out the C3 symmetry operation, our molecule superimposes. Now let's carry also out the C2 symmetry operation. And I have, in this case, rotated around this C2 axis. And you see that the molecule superimposes itself. I can maybe just repeat this. Okay. See that these 2 oxalates here are being swapped up. This one remains at its position, but the carbon atoms and the oxygen atoms within that 3rd ligand are also getting swapped up. So overall, we have D3 symmetry, and that means that we have the identity, the C3 as the principal axis, and 3 C2 axes as additional axes, but no other symmetry element. Okay. Now we can add additional symmetry elements to the Cn and the NC2 axes. For instance, we can add a horizontal mirror plane, and then we have the so-called prismatic groups DNH. So as the name says, the shapes of molecules that belong to this point group are derived from an n-gonal prism. Okay, so here, for instance, you have a pentagonal prism where n is equal to 5. Here, for instance, you have a hexagonal prism where n is equal to 6. Here, for instance, you have a heptagonal prism where n is equal to 7. So when we have this horizontal mirror plane in addition, then this creates additional symmetry elements. So we'll also have a number n of sigma v mirror planes. Okay. So for instance, when n is equal to 3, and we have, well, a C3 principal axis, then that must mean that we have 3 vertical mirror planes in addition to the horizontal mirror planes. It also means that we have to have an improper reflection operation of the order n. So what is a chemistry example for that? One example is the PF5 molecule. You know that the PF5 molecule has a trigonal bipyramidal shape. To which point group does it belong? It belongs to the point group D3H, because a C3 axis is the principal axis. It goes to the 2 axial phosphorus fluorine bonds. You can see it here. And in addition to that, you have now 3 C2 axes. So these C2 axes, you see here, they go to the 3 equatorial phosphorus fluorine bonds. Now, you must also have a horizontal mirror plane. So this is the horizontal mirror plane here. You see that this horizontal mirror plane stands perpendicular to the C3 axis, which stands here. So that horizontal mirror plane swaps up these 2 fluorine atoms, but leaves these 3 fluorine atoms unchanged. So now we must also have an S3, as well as 3 sigma V's. So the S3 you see here, it actually stands where the C3 is. Okay. So you see here the mirror plane associated with the improper rotational axis, which stands perpendicular to the improper rotational axis. And you see in addition here the 3 vertical mirror planes. Okay, so this is the first one here. Okay, this is the second one. And this is the third one. When you see that the 3 vertical mirror planes go to the 3 carbon fluorine bonds, which are equatorial. So this one here goes for this carbon fluorine bond. This one here goes for this carbon fluorine bond, phosphorus fluorine bond. And this one here goes for this phosphorus fluorine bond. Okay. Now, a special case is the linear point group D infinite H. So in this case, we have a prism that has an infinite number of corners. And a prism with an infinite number of corners, vertices, becomes a cone. Okay. So now in a cone, you have a principal axis, as you can see here, which has an infinite order because we can rotate around an infinitely small angle to make our cylinders superimpose. Okay. And that means now that you have an infinite number of C2 axes. You see one of them here that goes to the middle of the cone and go all around the cone. Okay. So you see here, in this case, all the infinite number of C2 axes of such a cone, which in this case contains the CO2 molecule. So now that also tells you what are the molecules that adopt this D infinite H symmetry. So these are linear molecules that are non-polar. For instance, dihydrogen, carbon dioxide, etc. Note that this is distinct from the point group C, infinite V, where we also have polar molecules, linear molecules, but these are all polar. For instance, CO or HF, molecules of this kind. So, what is left to discuss? Is the point group type DND. So in this case, you have a principal axis Cn, and you have NC2 axes. Okay. But in addition to that, you now have, instead of a horizontal mirror plane, vertical mirror planes. And the number of vertical mirror planes is equal to the order of your principal axis. For instance, if the order of your principal axis is 3, then you have to have 3 vertical mirror planes. So now these vertical mirror planes are always dihedral mirror planes, and that is because they bisect the angle in between 2 adjacent C2 axes. Okay. Now an example for that is the ethane molecule in staggered conformation. You see this molecule depicted here. So we have here our C3 axis that goes to the carbon-carbon bond. And now we have 3 C2 axes in addition to that, that goes to the middle of the carbon-carbon bond. Okay? So the first one stands here. The second one stands here. And the third one stands here. And each of them bisect an angle between 2 hydrogens and 1 carbon. Okay? So now there are 3 dihedral mirror planes which contain the principal axis D3, but bisect the angle between 2 C2 axes. Okay? So you see the first one here. Okay, you see it contains the C3. You see the second one here, which also contains the C3. And the third one is this one here, which also contains the C3. Okay. So now I see that each of the dihedral mirror planes, they contain 2 CH bonds. So for instance, this one here contains this CH bond and that CH bond. Okay, so this one here contains this CH bond and that CH bond. And the last one, this one here, contains, no, sorry, this one is the last one. This one is the last one. It contains this CH bond and that CH bond. Okay? And you see that these mirror planes, vertical mirror planes, they bisect the angle between 2 C2 axes. So for instance, this one here bisects the angle between this C2 and that C2. Can you see this? So these C2 have an angle in between, and this sigma V bisects the angle in between the two. Okay? And so do the other vertical mirror planes. So overall we have the identity, the C3, we have the 3 C2s, we have the 3 sigma Ds. So in addition to that, we also have an inversion center, which is generated by these symmetry elements, as well as a 6 axis. So we have to have generally an improper rotation reflection of an order which is twice of the principal axis. Okay, so now what is left? There is one kind of point group that we have not considered thus far, but I see actually I forgot to animate the molecules. So you actually just saw, what did you see? You see one of the C2 axes. So we actually rotate it here on this C2. Okay, and then the 2 carbon atoms swap up, and this hydrogen moves over here. Okay, this hydrogen moves over here, and this hydrogen moves over here. I can do this again. Okay, so we rotate around the center of that carbon-carbon bond. Okay, and because the C2 bisects actually the angle between these 2 hydrogens, basically these 2 hydrogens are being swapped up. No, I'm sorry, that's not correct. No, I'm confusing myself. Let's do this again. So this one moves over here. So actually they bisect the angle between, sorry, I was incorrect. So they bisect the angle between this one and that one. And that is the reason why these 2 are getting swapped up. Okay, so they bisect at the angle between 2 hydrogen atoms that belong to different carbon atoms. Okay, now what's left is the so-called improper rotational point groups. They are denoted S2N. And in this case, you have, in addition to the identity, a principal axis, and then an improper rotational axis that has 2 times the order of the principal axis, but no other symmetry element except an inversion center that may or may not exist. So here's an example for this kind of point group. So in this case, we have an S4 improper rotational axis that stands in the same position as C2 axis. Okay, so that makes the point group S4 in this case. So we see here that this molecule has alternate carbon-carbon double bonds and carbon-carbon single bonds. But this molecule is not planar, so 2 of the carbon-carbon double bonds are below the plane, and the other 2 are above the plane, and the other 2 are below the plane. And in addition to that, there are methyl groups attached here and here. So these 2 methyl groups are above the plane, and these 2 methyl groups here are below the plane. And then there are 4 additional hydrogens, so these 2 here, which are above the plane, and these 2 here, which are below the plane. Okay, so now the S4 and the C2 axes, they go to the center of this 8-membered ring. And then there's a mirror plane perpendicular to that. And that mirror plane belongs to the S4 axis. So it's not a proper mirror plane, it's an improper mirror plane. Okay, so now here you see the same molecule from a different perspective. You see again the 2 carbon-carbon double bonds, which are actually below the plane in these two carbon-carbon double bonds, which are above the plane, as well as the two methyl groups that are below the plane, and these two are which are above the plane. So now, as we have to carry out an S4 rotation reflection, we have to rotate, well, first by 90 degrees and then more perpendicular to that. So now you can understand that the molecule will superimpose its original form by putting yourself on a particular group. For instance, we can put ourselves on this methyl group here. So now if you rotate counterclockwise by 90 degrees, well, this methyl group will move into this position here. But it would still be above the paper plane. Only if we mirror perpendicular to the axis around which we have rotated, our methyl group will be below the mirror plane. And so that happens to all these methyl groups. Okay, so this one will be rotated into this position, this will be rotated into this position, and this one will be rotated into this position. Okay, now for all the other atoms, basically the same logic follows. So this one here will be rotated 90 degrees and then mirrored, and then it's in this position. This one here will be rotated by 90 degrees and then mirrored, and then it will be in this position. This one will be rotated by 90 degrees and mirrored, and then it will be in this position. And this hydrogen atom here will be mirrored, will be rotated by 90 degrees, then mirrored, and then it will be in this position. Okay, so the same will also happen for the carbons of this 8-membered ring here. Okay, if you rotate these two by 90 degrees, then they are here, but these two are then still above the plane, so we must mirror them in addition so that they're below the plane. And these two here are originally below the plane, so if you rotate them by 90 degrees, then they are in this position here, but still below the plane, so we must mirror them in addition to that they are above the plane. So here's a little animation from applied to this molecule here so that you can see how the molecules actually transform. And I don't know why sometimes the animations work and sometimes they don't. So I'm sorry, this animation does not work as planned. I have to work on that again. Ah, now it works. Okay, you see it. Okay, so now we have discussed all the point groups that there can be. And point group determination is an important skill a chemist needs to have, and this is also something that I expect from you in the exam. So with practice, you can actually just look at the molecule and knowing the properties of the different point groups, you can actually directly say which point group belongs to which molecule. But if you're not so familiar yet, there are actually guides that can help you with the point group determination. So these guides ask specific questions about specific symmetry elements and operations in a specific sequence. And you have to answer these questions either yes or no, and that guides you to a particular point group. Okay, let's do this by example. For instance, we can first use a guide which asks first, well, does our molecule have a principal axis with the order n? Now you need to look at the molecule and determine whether there is a proper rotational axis of an order n. Okay. So now the answer to that can be either yes or no. So now let us first assume that the answer is no. So if the answer is no, then you know that your molecule must belong to a low symmetry point group. Now we have learned that there can be different low symmetry point groups. So now you need to determine to which low symmetry point group your molecule belongs to. And to figure that out, you have to ask additional questions. So in our guide, you ask the next question, which is there an inversion center present? So again, the answer can be either yes or no. So if the answer is yes, then we know that our molecule must belong to the point group Ci. If the answer is no, we ask another question, which is, does our molecule have a mirror plane? So if the molecule has a mirror plane, then it must belong to the point group Cs. If not, then it must belong to the point group C1. So now we have probed for low symmetry point groups. Of course, it could have been that our original question, does our molecule have a proper rotational axis, would have been answered with yes. So if it had been answered with yes, we would have needed to go this way, okay, and ask the next question, which would now be, do we have 6C5 or 3C4 or 4C3 operations present? So by asking this question, we ask basically, does our molecule belong to a high symmetry point group? Because if it belongs to a high symmetry point group, then there would be either 6C5 or 3C4 or 4C3. So now the answer can either be yes or no. So let's assume that the answer is yes. So that must mean that our molecule must belong to a high symmetry point group. So now we need to determine to which high symmetry point group our molecule belongs. And to figure that out, we need to ask additional questions. So we can next ask, well, do we have 6C5s? So if we have 6C5s, then we must have icosahedral symmetry. Now, there are different point groups for icosahedral symmetry, and we must distinguish between them. So therefore, we ask the next question, which is, does our molecule have an inversion center? So if the answer is yes, then our molecule must be of IH symmetry. If the answer is no, then it must be of I symmetry. Okay, now it could have been that our answer to this question here was not yes, but no. In this case, we would have asked an additional question, which is, do we have 3C4 axes? So here we are asking for octahedral symmetry, because octahedral symmetry is associated with 3C4 axes. So now if the answer is yes, we again ask next, is there an inversion center present? And if an inversion center is present, well, then our point group must be OH. If our inversion center is not existing, then our point group must be O. So now if the answer to this question wouldn't have been yes, but no, we would have gone further into this direction and asked, well, do we have 4C3 axes? And if so, we would have a tetrahedral point group of the type T. Now there are 3 different ones, and we must distinguish which ones we have. In order to do so, we have to ask additional questions. So next we can ask, do we have a horizontal mirror plane in addition? So if that is so, our point group must be TH. If that is not so, then we ask next, do we have dihedral mirror planes present? So if we have dihedral mirror planes present, our point group is TD. If we do not have dihedral mirror planes present, then our point group is T. So now we have probed for all possible high symmetry point groups. So what's left? Well, it's the rotational groups and the dihedral groups. So if that question here had not been answered yes, okay, then we would not have a high symmetry point group. And in this case, we would have asked next, do we have NC2 axes that stand perpendicular to the principal axis Cn? So this question distinguishes between rotational groups and dihedral groups. So now there are again two possibilities. The first possibility is that the answer is yes. So in this case, we would have a dihedral group. So which dihedral group would we have? Well, we would ask additional questions in order to determine that. So the first question would be, is there a sigma h mirror plane? So if there was a sigma h mirror plane, well, the point group would be DNH. So if not, well, we would ask, well, are there dihedral mirror planes? If that is so, our point group would be DND, and if not, our point group would be DN. So now we have probed for all the dihedral point groups that there are. So now if that question here hadn't been answered yes, and we wouldn't have NC2 perpendicular to Cn, well, we would have a rotational group. So now we would need to distinguish which rotational group we would have. So we would ask additional questions. So we would first ask the question, well, do we have sigma h in addition? So if we have a sigma h in addition, well, our point group would be CNH. If not, we would ask, do we have vertical mirror planes in addition? If not, so if yes, we would have the point group CNV. And if not, we would ask, well, do we have an improper rotational axis, which is twice the order of our principal axis? So if this is the case, then we would have the point group type S2n. If that's not the case, then we would just have the point group Cn. So now we are finished, and we have probed for all the possible point groups that can be in our guide is now complete. Okay. So in the exam, I could give you this guide in its full form, and you would need to be able to determine the point group based on that guide. Okay, so now let's practice this by one example. So for instance, let's look at this molecule here. So this is a dibromonaphthalene, not an inorganic compound, but it doesn't matter. Symmetry applies to both inorganic and organic compounds alike. So let us apply our guides. So our guide says, well, first we need to see if we have a principal axis. So do we have a principal axis of the order Cn? Do we have a proper rotational axis? Can anyone tell me? We can do this example together. Can you see one?
There's an immediate C2, I guess. If you just rotate it 180, you'll get the bromines in the same spot.
Correct. So there's a C2 axis that goes through that carbon-carbon bond and stands perpendicular to the plane of the molecule. Okay, so our answer is yes. So that means that we do not have a low symmetry point group. So next we ask, do we have 6C5 or 3C4 or 4C3 axes present here? So should we answer this question yes or no? Any ideas?
No.
No. Okay, certainly We won't have that. So that means that we won't have a high symmetry point group. All right. So now we can ask the next question, which is, do we have n C2 axes that's then perpendicular to Cn? Yes or no?
No.
No, that's also correct. Okay, so that means that we must have a rotational group. So what's the next question? The next question is, do we have a sigma h? Can you see one?
Yes.
Yes, there's a sigma h, and it's just in the plane of the molecule. Okay, it stands to the C2 principal axis that goes through this carbon-carbon bond. Okay, and that means that we have found our point group, which is overall C2H. Okay, so I would recommend to practice this. So seeing symmetry elements and symmetry operations in molecules is a matter of practice. Either you see them or you don't see them. The only thing that you can do is understand what that symmetry element is and then practice seeing them. And over the time, you will get better with this. So now, last but not least, I briefly wanted to talk about chiral point groups. A molecule is chiral when it belongs to a chiral point group. So what makes a point group a chiral point group, and what makes a molecule chiral? So a chiral point group has only proper rotational symmetry, but no other symmetry except the identity. So that means that you can have, only proper rotational axes, the identity, but no other symmetry element. An equivalence statement is to say that a chiral molecule or a chiral point group must not have an improper rotation reflection symmetry element. Remember, rotation reflections or improper rotations include the mirror planes, because a mirror plane can be expressed as an S1, and it includes inversions because NS2 is the same as an inversion. Okay? So if the molecule has these properties, then the chiral molecule belongs to a chiral point group, and such a molecule must then have a so-called enantiomer to itself, which is the mirror image to itself, whereby the two mirror images cannot be superimposed. So an example is here. It's very simple. So you have here a carbon atom with 4 different substituents: chlorine, bromine, fluorine, and hydrogen. So now this molecule has no symmetry element but the identity. Therefore, it must be a chiral molecule. Because of that, there must be an enantiomer to it, which is its mirror image. And the mirror image is this one here. Okay, so we can draw a mirror plane in between these two molecules. Note that this mirror plane is not a symmetry element, so it's not a horizontal or vertical mirror plane. It's just a mirror plane between the two enantiomers. So if we apply this mirror plane, then we mirror this bromine to this position and vice versa, this chlorine to this position and vice versa, this hydrogen to this position and vice versa, and this fluorine into this position and vice versa. Okay, so these two cannot be superimposed no matter what you do with them, no matter how you rotate them. So really different species, different isomers, different enantiomers. So note that, for instance, this one here It's not a different molecule. So here also the substituents seem to be swapped up, right? So here we have the hydrogen in this position in comparison to that position, and the fluorine is now here instead of here. The chlorine remains at its position, but these two are not different molecules, they're identical molecules. And that is because in this case, I only need to rotate around the chlorine-carbon bond in order to make these two molecules superimpose, okay? I need to rotate basically clockwise here. That brings the hydrogen, rotate the hydrogen here, the bromine over there, and the fluorine over here, and then the two molecules are identical. Okay, sometimes molecules look symmetric, but they're actually not. So this one here looks fairly symmetric, but it's not. It has only one inversion center here. So is this chiral? The answer is no, it's not chiral because the inversion center exists here. Note that this molecule has carbon centers with 4 different substituents. Okay, so look at this carbon, for instance. It has this chlorine, this bromine, this hydrogen, and then this 4th substituent here. But nonetheless, it's not chiral because it has here an inversion center. Okay, so the criterion of a carbon having 4 different substituents is not enough to determine chirality. You really have to determine whether there are improper rotational inflections in addition to identity in principal axes or not. So chiral point groups also not necessarily need to be low symmetry point groups, and chiral molecules not necessarily need to be low symmetry molecules. Because there are high symmetry point groups, and these are the rotational subgroups of the high symmetry point groups, which only have the identity in proper rotations, but no rotational reflections. Okay, we learned about that previously. So this tetramer cluster here, for instance, that we looked at, belonged to the point group T, which is a rotational subgroup of TD, and has only C3 and C2 axes in addition to the identity, but no other symmetry elements. Okay, that makes this molecule a chiral molecule. Okay, the same with this molecule here, which belonged to the point group O, which is the rotational subgroup of the point group OH. Here we have only C4, C3, and C2 proper rotational axes, but no other symmetry elements. And that means that this cluster here must be chiral. And last but not least, we discussed the snub dodecahedron here, which belongs to the point group I. So the point group I is a rotational subgroup of the point group IH. So we have only C5 proper rotational axes, C3 proper rotational axes, and C2 proper rotational axes, but no other symmetry elements. Okay? So despite the high symmetry, we have still a chiral object. Okay, then let's stop at this point, and we can maybe stop the recording here.